Hello, these are the review slides for exam 3 on for the summer 2017. Look at that. So again, these are going to be the free answer parts. Look at that. And so the first thing up, or determine the E and Z configuration for alkenes. Look at that. So we're still going to use the same priority rules that we did for the R and the S, the Prelog rules, or the Kahn-Ingold. The Kahn-Ingold Prelog rules, stuff like that. So, but here what we're going to be doing is we're going to be assigning for basically high and lows, or you can think 1 and 2, for this carbon, and then figuring out 1 and 2 or high and low for this carbon. So really what we're going to be doing is just slicing in half, figuring out this side, figuring out this side, and then looking at see which side the higher priorities are on. So for that, so for this one here, right? So for this side here, right, we're going to be comparing chlorine to nitrogen, right? So this has a higher priority, so high, low. So then we look on this side here, right? So we have a CH2 and CH2, just regular methylenes here. So this is going to be a tie, right? So with that, so carbon carbon, right? So you'll both have 2 carbon carbon, 2 carbon hydrogens, right here. Again, 2 carbon carbon, 2 carbon hydrogen. It's going to be a tie. So then we have to look at this one and those two. Right? This one only has 1 carbon carbon, 3 carbon hydrogen, right? Because it's CH3. So there's another CH2. So we got 2 carbon carbon, 2 carbon hydrogen, right? So with that, so this is going to be the high and the low. High, high, right? So they are on the same side, right? So with that, and so it's going to be Z, best German accent. So with that, okay. So for this side, we're gonna slice this through. So we're gonna look at what's going on here, right? So this is we got a carbon attached, hydrogen attached. So here we've got your high and low on this side, right? So you have a CH3, CH2. So for this one, we've got 1 carbon-carbon bond, 3 carbon hydrogen. Here we have 2 carbon-carbon, 2 carbon hydrogen, right? So, so here and here, right? So this chlorine didn't even come into play. So for this one, this is the high, this is the low. Okay. So notice that the highs are on opposite sides, so it's E. Okay, so you're going to have to draw one of these mechanisms, stuff like that, and so I'll give you a reaction like this. It'll look just like this, and we'll be saying, tell you, draw the mechanism. Okay, so for the so just as a reminder, the SN1, E1, so the ones happen in 2 steps. The SN2 and E2 all happen in 1 step. It's kind of just so happened to work out that way. So the first step for the SN1 and E1 is always going to be the same. It's going to be the leaving group leaving. And so you're going to end up with the carbocation here, right, plus Br minus. Okay, and since it's an SN1 mechanism, we're going to get substitution. And so for here, this is going to, the nucleophile here is just going to attack the carbocation to give you that product. So that's it. So that, so if there's an SN1, right, we get backside attack, kick this away, all in 1 step. If this was an E2 or E1 or E2, we'd be having the cyanide here attack one of these the CH bond, say here or on this side, ripping that away to make the double bond. But here it's an SN1, so you're just getting substitution. Okay, so you'll also get a mechanism for a hydride shift. Okay, so you would expect, if this was a regular elimination, to have that double bond be here, but in fact it's over here. So let's indicate that. Yeah, I know this E1 is not going to happen on a primary carbon, but it's just an example. So we're just going to go with it. So like this would go away, right? Because it's an E1, so that has to go away. Right, it's usually the carbons of interest. It's usually a good idea when you're doing a mechanism. Go ahead and draw on those hydrogens. Right, so Br minus, right. So now the carbocation is right there. Right, this carbonyl only has three on it, so it's got a carbocation. But if we shift this hydrogen over there, we're going to get a now we're going to get the carbocation there. So this hydrogen is shifted over. Now there's 3 hydrogens there. Since we know that the that we need to take the hydrogen from that side, the OH minus is going to grab this hydrogen, and that's going to collapse there to make this. There we go. So how do I know it took this hydrogen? Because because the double bond happens between these 2 carbons, so that's where the double bond has to be. So the carbocation is going to be on one side, the hydrogen you remove is going to be on the other. There you go. Okay, so there's going to be a problem where you're dealing with a cyclohexane and an E2 reaction with that. And so for here, if you remember for the substitution and elimination reactions, this the leaving group has to be in the axial position, because what's 180 degrees from here is actually this carbon that carbon-carbon bond right there, which you can't use. So if this is in the equatorial position, you're going to need to do a chair flip with that. So keep those 2 the same. Right now this side goes up, it goes down. So for so let me number these: 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3, 4, 5, 6. Okay, so 1. This was the bromine was equatorial, so now it's axial, right? So the carbon-carbon bond's pointing axial, so you're pointing straight up. Well, that's good. This on carbon 3 there was a methyl group. Right, now this is axial, right, because it's pointed, carbon-carbon's pointed down, so that means the axial is straight down. So now it's equatorial, so we're just gonna kind of put it over here to the side. Okay. So for here, right, there's an axial and equatorial hydrogen. Same thing here. There's a hydrogen on this side as well. Well, if we go on this side, right, there's a bromine axial up, there's a hydrogen axial down, so that's going to make to have the double bond here, right, in your equatorial CH3. If instead you made the bond there, right, the double bond would be here. CH3. So you get 2 products. Okay. So there you go. The big thing here is if that leaving group is equatorial, you got to flip it to axial. Okay, so design a synthesis. Okay, so what we're going to do is we're going to say, okay, we need to create this molecule using these carbon components. You can use how many or whatever you want. Okay, and so the trick to this is to say, okay, where are we going to find, where are these components here? And so if you notice this part here, right, it's just a 2-carbon piece, or an alkyne with a hydrogen sticking off of it. Okay, that would probably be this one here. Okay, so and then that would leave these two carbons here. So we need a 2-carbon piece to be able to attach this. So we're in fact going to need that part there. And so how do we know how to make carbon-carbon bonds? Well, we start off with the with your alkyne, add sodium amide. Okay, that's gonna rip this hydrogen away, and those electrons are going to go here. It's just a normal acid-base reaction, and so you'd end up with that. So these 2 electrons here become this lone pair here. Okay, and then you're going to dump in the ethyl bromide there. Right, here's your 2. There's your 2 carbons. Right, you just get an SN2 attack here to here. So you'd end up with right? 1, 2, 3, 4, right? 1, 2, 3, 4. So there you go. So this is what I'm looking for here. Can you take these molecules and make that component there, or that product there? Okie dokie. So you are going to need so reactions to know. So you understand the SN1, SN2, E1, and E2 reactions. Know what you're asking. I give you a predicted product question. I need to see it. You need to know Zaitsev's rules, where the for an elimination reaction you want as few of hydrogens on that double bond as possible. You also need to know the stereochemistry of the SN1, SN2 reaction. So with SN2 you get inversion. For the SN1, right, you get both the R and the S. You both get both the wedge and the dash coming out. So you're going to need to know that. That's all going to be here. Okay, so reactions to know. So this is an example reaction, and then this here is just an explanation for what is going on. Okay, so here you can have sodium hydroxide. You could also have potassium hydroxide. With that, right? So this is an E2 type mechanism, right? So you have to look on either side, right? So there's a hydrogen here and a hydrogen here. So you could make a double bond here, right, which would be this product, or you can make a double bond here to make this product, right? So the leaving group was originally here and here. Okay. So if you want to do it under acidic conditions, it's the exact same thing, but now your leaving group is an OH. This is going to attack here, and you turn your OH into a water molecule, which is a really good leaving group. But again, you're going to get the same effect, right? So that's where you're going to go on this side and this side. Okay. Now with hydrogenation, so with alkenes, all you do is you put hydrogens across here, and the effect is going from double bond to single bond. Okay. If you have an alkyne, you do that exact same reaction. It would go through this intermediate here, the alkene intermediate, but that's still reactive, and so you would go all the way down to the alkane. Okay. So if you want to stop it at the alkene, what you need to do, there's two different ways you can do it. With the hydrogenation, what you have to do is use that poison catalyst, either a Lindlar or palladium with barium sulfate. That will stop it. But because the hydrogens add to the same side, you're going to end up with the cis product, or the cis double bond here. Well, this is cis product. If instead you use lithium ammonia or sodium ammonia, you actually use a different mechanism, and so this generates a trans double bond, right? So there's one up, one down here, one up. They're both on the same side. More reactions to know. So this is just talking about the design of synthesis one, where you can take the sodium amide, it'll rip off this this hydrogen here. It's the hydrogen right next to right on the double bond or triple bond, right? So it's just this one. So there is a CH3 here, right? But that carbon hydrogen bond is way too strong for the sodium amide to take off. It's just this one here. So then this can come in and do just a nice SN2 attack, kick that away, and now you got yourself a new carbon-carbon bond. So that's all this is showing. Okay. So predict the product, right? So we know, I want to see an SN2, so I'm going to tell you which kind of product I want. So for here, right, you're going to get backside attack for there. You are going to get the substitution product. Okay, but so you're going to swap in the OH for the BR, but with an SN2 you get inversion. So if the leaving group's on a wedge, what you put in is going to be on a dash. So it's like that. Okay. So for an E2 reaction, right, we need a double bond. Okay, so here's our leaving group. Okay, so we need to look. Are there hydrogens here? Yep. Are there hydrogens here? Yep. Are there hydrogens here? Yep. You look all around. Okay. So if you're gonna make a double bond here, you'd make this product. If you're to do it down here, right, you would make this product. If you do it right here, you'd make that product. Now, this product and this product are in fact the same, because if you just take this molecule and flip it over, it turns into that. So you really only need one one of these two. But between these two, which is the major product? Well, on this double bond, we don't have any hydrogens on this carbon, but we do have one on this side, right? One hydrogen. On this one, we don't have any on this side, but we have two hydrogens on this side. So two hydrogens. You want as few hydrogens on there as possible, and so this is the major product. Okay. Now for this one, okay, the you have you're doing a hydrogenation, right? So with that a triple bond, but because we have a poison catalyst, what's going to happen is we're going to take out one of these double bonds and we're going to add the hydrogens on the same side. Okay, and so if you wanted to be real fancy with the it would look like this, right? Because the hydrogens are on the same side. I need to, so if you were to draw it like this, I'd take it. This is probably a better way of doing it, but you need to indicate to me that for this one, you're putting them on the same side. So, good luck.